All right, so the first thing you should note is that in these situations, these two examples, unlike the first three that I drew, not every point is in the domain of these vector fields. You see that? Because you have x in here, right? So that means this entire line called, what do you call this? Where x is equal to 0. Here, let's go ahead and use my different color here. Yeah, this entire line where x is equal to 0, we call the set of these points simply as y, the y-axis. Right? The y-axis is off limit. In other words, every point on the y-axis is outside of the domain of this function. So we will not draw any arrows where x is equal to 0. We can't, okay? So when x is equal to 1, let's think about when x is equal to 1, right? So here, this is a 1, 0. And by the way, if x is equal to 1, you may want to jot down these things sometimes for these more complicated vector fields. If x is equal to 1, right, then f of x is going to be 1 something, right? It's 1/2 y. So at this point, it'll be, because this point is 1, 0, it'll be 1, 0. And you draw 1, 0. This is a point 1, 1. So it's going to be 1, comma, 1/2 of 1, which is 1/2. Okay, so this is, yeah, this is the vector 1, comma, 1/2, right? At this point, okay, what is that? This is 1, 2. At that point, then it'll be 1, and then half of 2 is 1, so it'll be this. And then this is 1, 3, so it'll be 1, comma, 3 over 2. That's 1, comma, 1.5, right? And the same thing happens here. This will be, the y-coordinate here is -1. So the y-coordinate of the vector that results as an outcome is -1/2. Okay, and at this point, it'll be 1, -1. Okay, I think you get the idea. And by the way, if you go to this side, x is -1. So 1 over -1 is -1. And so everything is going to go in this way. Oh, that's probably not right. Okay, so here, this is -1, 1. So it'll be -1, comma, half. And here it's -1, comma, 1, and so on. Okay, hopefully you see that the symmetry is pretty visible here and pretty clear. Right? And once you see the symmetry on both sides, then that will help you draw these vectors. Okay, so this is 1. And then maybe you can try when x is equal to 2. So here is the point 2, 2. Okay, so what is the output at 2, 2? Well, it's going to be 1 over 2. And then 2, 1/2 times 2, which is 1, right? So at this point, it'll be negative, 1/2, 1. It'll be like this. Okay, and so at all of these points, where x is equal to 2, the first component will be 1/2. So it'll start to look, this way. So maybe I should do one more. At this point, yeah, okay, that would be, that's not, okay, how about this point? 2, 1 is this point. So it'll be 1/2, 1/2. Okay, and you don't have to draw a whole bunch of vectors when you are asked to do this. Sometimes, you can, here I've drawn more than 10, but it's not necessary to draw that many. If you do maybe 9 or maybe even 6, that is sufficient. All right, so I should say undefined on the y-axis, okay? All right, how about this? X over, what is going on here, right? Now, if you think about this, here is your first coordinate, here's the second coordinate, right? Think of what happens if you called, let's see, I don't want to use X and Y anymore, right? But if you think about this, if you square this, you get this. And if you square that, you get this. And if you add the square of the first coordinate and the square of the second coordinate, guess what? You will get 1, right? And the square root of this is, of course, 1. So this means every vector, and you may have noticed this, every vector is actually a unit vector. because you're dividing by x squared, square root of x squared plus y squared, right? All right, so whatever you draw at any place is going to be a unit vector. And that's nice to know, right? So none of these vectors I'm going to draw will be longer than the other ones. However, this is not defined at one point. Where? The only point where this is not defined is if the denominator is 0, and the denominator is 0 only at one single point, which is at the origin. So at this point, I'm not going to draw anything. Sorry, how about 1, 0? Okay, it'll be 1, 0 in that direction. This is a point 1, 1. Okay, so 1, 1 will give you the vector, which is 1, comma 1, and then divided by the square root of the length, square root of x squared plus 1 squared. Right, so this will be a vector of this form, length 1. It's basically going to be 1 over square root of 2, comma 1 over square root of 2. At this point, 0, 1, the vector will be 0, 1. And so you will see that at here, all of these are going to be unit vectors, as I said before. And even at this point, this, let's say 2, 2, it'll be in the direction of 2, 2, right? But it'll still be a unit vector. It's not going to be as long as in other cases here, right? So every vector will be a unit vector going away from the origin, okay? So that's the kind of vector fields we are talking about. All right, and then one more type of questions you will see a lot of in homework is find the gradient vector field for a given multivariable function, right? So let me give you a function here where f of xy is x squared y plus 3y or something. All right, so what do you do that? Well, all you have to do is really this. Capital F, which is our vector field, is the gradient. That's what it says, gradient vector field. So all you have to do is find fx and fy for this particular f, which is 2xy, comma, x squared plus 3, right? And that's all you have to do. Sometimes I think for some homework problems, it's a little more complicated. But you know all about this because you studied this back in chapter 4, I believe, right? So this is all you have to do. Just find the gradient and you'll get your vector field. All right, so this is pretty much it for section 1. But however, don't finish yet. Section 2 is really, really long. And the part of the why it's so long is because they introduced to you 2 applications of vector fields. So let me just go ahead and get started on these 2 applications. Okay, one is called work, 4-letter word, W-O-R-K, and the other is called flux, another 4-letter word, F-L-U-X, right? Because those 2 are the primary things that you will be integrating in this chapter, all right, in this chapter on vector fields. All right, so let me explain. Okay, so work and flux. Okay, so these are like I said, these are the 2 main integrams, and both of these have to do with vector fields. So 2 main applications of vector fields. All right, so let me give you vector fields. I'm going to draw a vector field or 2, and then I will talk about these 2 ideas just very quickly. All right, so imagine you have this vector field, which let's suppose that these black arrows indicate the wind, or let's say current, okay? So you're looking at a part of the ocean, and this represents a current of the ocean water, okay? And let's say your boat is going from here, and you're going to go this way, right? Your boat travels from point A to point B in this direction. And you can see that wind is actually pushing you almost all the way here, right? In fact, even at the very end, maybe at the very, very end, you're going against the wind, which you can do on your sailboat if you know anything about sailing. But anyway, your wind is sort of helping you out, right? You're pushing it from the back so that you can easily and quickly go from point A to point B. The question here is how much work is done by this wind described by this vector field as the boat goes from A to B, right? Well, the thing is, work is basically the, what is work? Okay, work is basically distance times the force, but the force is in that direction. Let me just go ahead and write this down. Work is basically the force times the distance. But the better description of this is as follows. All right, so let's say you have this floor and you have this box that you are trying to pull. All right, and so you're pulling, but you don't pull in the horizontal direction. Your force is kind of pulling in this way because this box is on the floor and you're tall and you're pulling it. Right, and if you draw, let's say you move this like I'm going to draw another one here. Let me just go ahead and do this. I think this is good. Okay. All right. So the direction in which the box is moving is actually this. And I'm going to indicate this as a unit tangent vector, capital T, if you remember what that is, right? Okay. So let's say you move this 10 feet. Okay. And you are pulling this at the force F. That's your vector field, okay? But the point is, even though you are moving this with the force F and force is exerted to this, not the entire force is acting to move this thing, right? What you have to do is to project it down to this direction, and you have to calculate this component of the vector, and that vector, the magnitude of this vector is the force applied in moving this object box from this point to that point. Okay, now at every single point as you move this at 10 feet, you are moving this with a force of F at this angle theta. All right. So in this case here, let me ask you this. In this case, what you have to do is as you move from A to B, here's a point. Okay, here's a point, and the wind is moving in this direction, but only the component of the direction parallel to your motion is going to be calculated, and that's what you have to integrate. Notice here at every single point, you can calculate the parallel component, okay, the component of F parallel to the tangent vector, because you are moving in the direction that is tangent. I mean, that's the definition of the tangent. Okay, so does this make sense? At every single point of this path from A to B, you can evaluate how much what the magnitude is for the component that is in the tangential direction. All right, so that would be this this vector that is drawn in blue. Okay, well, let's try to figure out what that force is. Okay, what is the magnitude of this force parallel to or in the direction of the motion? So what I'm trying to say is this distance is, okay, that's 10 feet, but this force is the force in the direction of the motion. Okay, this is the important part. So we need to find the length here. Okay, so let's try to find out what that length is. That length is going to be the magnitude of F times the cosine of theta. Do you agree with that? Yeah, so this force is exactly that, right? Because that would be the length of this blue arrow, okay? So it's the magnitude of F times cosine of theta. But wait, this looks familiar, right? Note, F dot T. Okay, what is F dot T? Well, that's the norm of F times the norm of T times the cosine of the angle between them, which we indicated as theta. But guess what the norm of capital T is? This is the unit tangent vector, right? So it is actually exactly what we want. It is the magnitude of F times cosine of theta, okay? So this, at every single point of this motion, okay, F dot T, so therefore F dot T is the force at every single point of this motion. F dot T is the force in the direction of movement or the motion. Okay, so when you dot F, the vector field, with a unit tangent vector in the direction of the motion, then you get the force acting, or force that is acting on the object at that point in the direction of capital T. And therefore, if you integrate this, okay, so therefore, if you integrate this over that path, the curve C, all right, this is the curve C. The C is the curve or the path from A to B, right? If you, because see what happens is, you know, every single point, at every single point of this path C between A, from A to B, you can find the tangential component, which is this, you know, blue arrow, the tangential component of the vector field, which is applied in the tangential direction as the boat moves from A to B. At every single point, you can calculate it. And guess what the integral is? An integral is a continuous addition, right? So you can add every one of these real values along C, and that is called the, what we'll be defining this in next section. This is called a integral along the path, or um, line integral. Technically, it should be called a path integral or curve integral, right? And that curve integral will be defined as an integral with a C here of f dot t. And we don't use dx dy anymore. It'll be ds, which is to be explained later, but it is the a new differential, okay, along the s, which represents the arc length. More to come in the next section. So this is actually the integral of all the force in the tangential component, which means the direction of the motion. And if you integrate that along C, you get the total work. Work of what? Work done by the vector field F along path C. Okay, so that is why this F dot T is an important thing. This, by the way, because the dot product is a what? The dot product is a real valued function, right? So this is a real valued function. The answer will be a real number, which represents work, okay? And that's why, that's one of the major applications of a vector field. Again, vector field dotted with T will give you what is called the tangential component, which if you integrate it, will give you work, all right? All right, the second application, that was half of my comments here. The second one is flux. All right, so this time, instead of thinking of a boat going from A to B, let's say this time we are going to talk about this. Okay, so this goes from A to B, and we can call this curve. This looks like a straight line, but it's a curve C, and this path is some sort of a film or a filter or a membrane. Okay, lots of ways to say this, but what is a filter or a film or a membrane? It's something that would allow certain things to be filtered through, right, going across. Like for instance, right, if this vector field, these arrows represent the flow of a fluid, you can see clearly that it's going across here, going across here, going across here. Over here, it's going the other way. Over here, it's going, but slightly. If the flow is, if it's parallel to the path AB, then nothing is flowing across from, from this side to this side, right? So the amount of flow can be calculated if you look at, along every, let's see, at every single point of this, you are going to look at how much of this fluid is flowing from this side to this side, this side to this side. Okay, that is what you need to do. But again, depending on the angle at which this arrow is in contact with the curve curve C from A to B, it determines the angle, and the magnitude of these arrows determine how much is going across. All right, so that is called the flux, or the penetration of the fluid from one side of the path C to the other side. Okay, now I'm going to draw another picture here. This time you have a membrane, or let's say this is like a ground. Okay, and I think you'll get the point. Ground is like a filter or film or membrane. And let's say the rays, the sun, the rays, the sunshine is coming this way, like this. Okay. So at noon, let's say like in July or June or something, the sun is way, way high. And it's hitting the ground at this point. Okay. Do you know how much heat or let's say if this is the sun, if it's going to be the heat absorption. If this is radiation, then it'll be the absorption of that radiation energy at this point. Okay. What is that point? What is the amount absorbed by ground at this very point of the ground? The answer is, and maybe you know this, it's really this much, right? What do we mean by this much? It is going to be this vector projected onto the vector that is perpendicular to the ground. Of course, perpendicular means normal, right? We call this capital N. So let's say this is capital N, and I'm talking about, of course, the principal unit normal vector. Okay, so if you just project it down to this, down, or in this case, across to the capital N, that and angle between that is theta. Okay, so let's say this is your vector field F, and you take the projection onto N. That is this component, again, written in blue. This component, the length of this component is what we call the absorption or the penetration at this particular point. Okay, now compare this to another picture. If you have this ground here, ground is sort of in ground color, it's sort of brown. If the sun is way down, like sunrise or sunset, so the angle of the sun is very, very small, like this. How much of the sun's heat energy is penetrated or absorbed by the ground? Okay, the answer, you still have this N perpendicular, but only this portion, that's this portion here. Okay, and that, by the way, explains why in winter it's colder. Okay, and not to mention of course, the length of the day, daytime is shorter in the winter, but when the angle is really small, okay, when the angle of the sun is really small, then the ground is not absorbing as much heat. Okay, and this is true with lots of things. If you're talking about the fluid going across a membrane, or if this is not the ground but the surface, and you're trying to heat this up with some sort of irradiated heat, or if you're trying to let the radiation go through some sort of filter or something. Okay, how much is absorbed, or how much is going across from one side to the other, right? Well, you think of the absorption or penetration at each single point, and the answer is that it only goes as far as the projection, the projection onto the normal component. Okay, well, see, let's try to find what this normal component is. And that's going to be very similar to what we did, okay? Because the length of this vector, the blue vector, is going to be the magnitude of capital F, which is the magnitude of the vector field, times the cosine of theta, right? Okay, but again, note that F dot N, in this case, N being the perpendicular, a normal vector to the ground or to the path C, F dot N is the magnitude of F times the magnitude of N times the cosine of theta. And of course, you know what comes next. The magnitude of unit normal vector is simply 1. So this is the magnitude of F times cosine of theta, which is exactly the amount of penetration or amount of the flux at this one particular point. right? And of course, the ground is absorbing, every single point of this ground is absorbing the heat energy, right? And at every single point, this value is the same if F is constant, like in this case, right? But if F is not constant, okay, so if F is, here, let me change F to be non-constant. All right, so if these red arrows, which are the vector fields, are not constant, at this point, only this much is absorbed. At this point, it's this much is absorbed. At this point, it's this much is absorbed. Okay, so at every single point, you can define the normal component of the vector field F, and that's what you will be adding. Okay, again, remember, integration is continuous addition. It's a continuous version of the sum. And so you will be integrating at each point. You integrate over this path C, or the curve C, and that's going to give you the total amount of flux, right? So the parallel thing over here is this: F dot N is the flux at each point in the and the flux, of course, means it's the amount perpendicular to the vector, the curve C, right? So if you integrate F dot N, which is a flux or the flow at every single point of this curve C, and if you integrate it along C, this will give you the total amount of penetration, which is called the flux of this fluid or whatever this is across the path path from A to B, which is called C. All right, so I hope this is clear. When you integrate F dot T, where T is the unit tangent vector, you get the work done by the vector field along the path C. When you integrate F dot N, then you get the flux, which is the penetration of this object or the energy or fluid across that curve C from one side of C to the other one. Okay, so work is the integral of F dot T, and the flux is the integral of F dot N. We'll be spending a lot of time on F dot T and F dot N throughout this chapter, and that is really at the center of vector calculus or vector analysis, which is the major topic, which is what chapter 6 is all about. Okay, so section 1 itself is actually short, and I added that extra section or extra thing at the end about the flux and about work, but that should make section 2 a little shorter. Remember, section 2 is a very long section. You can read those many pages, but I think by doing this ahead of time, I think I can make section 2 a little more manageable. All right, so next time I'll see you when I explain section 2, which is on line integrals. And we'll be talking about different ways to establish and determine and evaluate line integrals. Until then, I hope you have a great week. I'll talk to you later. Bye.